Good afternoon, everyone. Hope you're all well, and thank you for joining. And I'm really excited to be here and joined by Lee, who's a software engineer with Yelp, one of our amazing Athena Hackathon sponsors. And before I pass it on to Lee, just a quick note for everyone watching. If you have any questions throughout the webinar, just kind of feel free to put them in the chat. I'll be keeping an eye on the chat throughout the webinar, and then we can have kind of a quick Q&A session at the end. And that's it. And yeah, over to you, Lee.
Thank you. Thank you very much. Hi, everyone. I'm Lee. Today I'll be talking about who are the MLOps. It's a talk about continuous integration within the ML domain. For those of you who are not that familiar, ML is machine learning. So at Yelp, we do a lot of machine learning, artificial intelligence. We train models. We use them in production. I'm a software engineer in the core ML team. So a little bit about me. I specifically work in the ML compute side of ML team. And it's a team who supports various ML projects within Yelp. And we provide the compute infrastructure and continuous integration for all these projects. So we're very much the infrastructure layer for all the machine learning teams. Cool. Right. So before we start, I would like to know a little bit about the backgrounds of everyone who's watching. I know we're virtual, so I'm not going to let people do a show of hands. But just kind of keep in mind, you can reply on the chat if you wish, or you can just kind of think about it. The answers to these questions, I guess there are a few basically to gauge where you are at with the ML domain and also the MLOps domain specifically. So I guess for the audience, who is an ML already? Maybe this is not the talk for you, or maybe it is. I mean, there's always something new to learn anyway. Who works with an ML op actively? This will probably be the perfect talk for you, as we'll dive into various aspects of the life in ML op. I guess also who's a DevOps already. DevOps is very much similar to what we do, with specifics obviously more dedicated to machine learning, to the algorithms, to the high intensive compute. If you work with a DevOps team actively already, you might be familiar with some of the concepts I will be talking about already. I guess the last question would be, who works in a data or ML orientated team? This would also be a good talk for you to kind of learn about the basics, and as well as kind of if you have any sort of specific questions, feel free to ask them at the end of this presentation as well. All right, so I mentioned DevOps before. I guess I think the concepts of DevOps really started from CI/CD, so continuous integration, continuous deployment, with the development of Docker, with the sort of all the deployment engines you have nowadays, whether it's Jenkins, Travis, Circle CI, those things. It's making it possible for us to do continuous integration, not worrying about having to deploy something in 3 months, have a timed deployment, everyone's on for maybe 24 hours monitoring it. Nowadays, it's very much, we write some code, we merge it to master, the pipeline will take care of everything. If tests fail, it won't be deployed. If the build is successful, it'll be deployed kind of automatically, and the whole circle, as is shown on this graph, kind of continues automatically, and the iterations we're going through are much more rapid and continuous compared to the sort of waterfall process in the past. So in terms of what traditional DevOps do in this field, we typically DevOps build these pipelines to enable the continuous development and deployment, continuous integration, as well as, I guess, quite often we provide the infrastructure for these deployments, for the testing of the services, and for the monitoring after deployments as well, so that we can have a smooth transition from the user's perspective. Everything is smooth, and it's almost like nothing happened. A new version is just there. So at this point, you might question, why do I talk about DevOps? How is this kind of linked to, with ML services? And effectively, what does a machine learning ops do in this case? So let's, I guess, let's think of a typical machine learning project. For instance, let's say in Yelp, we typically work a lot with restaurants, small businesses. So let's say we need a machine learning model that distinguishes, that basically labels or classifies user uploaded photos. And to make it simpler, let's say we only have two types of photos. They're either dishes or they're either beverages. So they're either a plate of food that you eat, or there's some sort of drinks, cocktail, red wine, rosé, whatever, right? So in this case, we're just trying to build a model that basically would classify all these photos. So for this, what do we need? We need the following. We need some training data, loads of photos, ideally already labeled, either by users, or you could hire a manual team to label them. You can use potentially mechanical Turks, things like that, and an operation team. There's loads of things like that online available who would label the things for you. And also, you also want to save some of those photos already labeled as a set of test data. And then also, we would need a machine learning algorithm. It might be some sort of binary classification, or it can be anything. It can be something more fancy, right? Maybe in this case, it will be a decision tree, potentially, a gradient boosted tree or something like that. So with all of the above, we should get an ML model. I work a lot with Spark. So in some of the slides, you will see basically Spark specific machine learning terms. But I also try to make sure it's accessible for other folks who are maybe not specifically using Spark and using other ML libraries or sort of packages. So I also try to put them in the slides as well. But if you're familiar with Spark, an ML model is typically referred to as a transformer, and a learning algorithm is typically referred to as an estimator. So we have all of the above, and we should, hopefully, fingers crossed, get a model which can then predict whether a picture is a type of dishes or a type of kind of drinks. So architecturally, this would look like, firstly, we need to collect the data. During this process, we either label them, or maybe it's already labeled data. You could do this with various kind of tricks. Quite often, for instance, a lot of mobile apps have these sort of integrations where they prompt users to nudge the users to label the data for them. So they might say, can you type a name for this photo? Or they might say, can you pick what is the type of this photo? Or in a kind of seamless experience, ideally. Sometimes you would also see in A/B testing, there will be like hidden kind of reviews for certain UI designs. All these are kind of manual labeling that you could get out of just the user for free, typically. However, if the scale of the data is really vast and you really need that much data, you could also consider sort of manual labeling and hiring external labor for those labeling. So we collect the data first, and then we try to train them. So we use a learning algorithm to train a model. And obviously, we would have some sort of split, the train test split in the data, so that with the test data, we can then use to test the model we've already trained. Once the model is trained and tested and it surpasses a certain accuracy, then we can deploy the model. And afterwards, we would then need to monitor how it is kind of performing on real world data. And typically, this can be done either manually again or sort of automatically. The new sort of images, for instance, if we're trying to classify whether it's a drink or type of dishes, when they come up, basically you can either then manually label them again and compare to the model output, or you can also use potentially a secondary model or something like that to monitor the performance of these data. Eventually, hopefully, the cycle continues, and as so there might be dependent on the project you're working on, there might be another kind of line coming out of the monitoring and goes back into the data collection, and it becomes a cycle that you continually work through. So we have all of that. Now what? What I've described as, I guess, done by typically ML engineers already. So why do we need ML ops? It sounds like as long as you have the data, you have the training algorithms, you should be able to just hire a few software engineers to do that already, right? Yes. But there is quite often a demand for machine learning ops. Let's say we have more than one project like this. There might be a project that classifies drinks versus dishes. There might be another project that tries to rank various services. There might be another service that tries to recommend, for instance, the restaurants to the users. So we might not have just one machine learning project in a company typically. So if that is the case, there will be a lot of common threads in all these projects. And we definitely do not want to reinvent the wheel. So this is when kind of it's necessary to have a team dedicated for the infrastructure layer, for the common layer that is shared by all these teams. And also typically, whenever we engineer any sort of features, we want to make them as reusable as possible so that they can be also shared amongst different teams. To give you a simple example of what is a reusable feature, let's say what is the location of the restaurant, right? That might be used in one project that's doing the recommendation. That might be then used in another project, which is doing, for instance, the ranking. So Also, sometimes we want to build new models, even with the same existing data. All these kind of new iterations, we can reuse a lot of the things we've already built. And this is really when a horizontal layer across all of these teams would be useful. And that is typically the whole responsibility of MLOps teams. So I showed you a diagram a few slides ago about the typical journey of DevOps and what continuous integration looks like with CI/CD. So it's usually build, test, deploy. Quite simple. But with the introduction of models, there is a few more stages. We're more data sensitive. We need to train, and we also need to validate a lot more. In the traditional DevOps land, the validation is typically just unit tests, integration tests, end-to-end tests, and things like that. But with machine learning, it's very much about validating the model itself, how it performs on the data sets. Also, sometimes the validation is also on the data set itself. We need to determine what sort of distribution the data has. Unfortunately, there's even more validation and testing needed after the deployment as well, because you typically need to know if the model has drift, if there's any sort of performance degradation. Let's say maybe iPhone released a new iOS version and they changed the default of your filter or some sort of like algorithm in terms of when you take a photo, the rendering is slightly different, which causes the image has a slightly difference in distribution of the RGB sort of pixels. Then in that case, you might see a degradation of the model. That is typically a case of not having enough training data. You should expect it to improve when you have more and more data and it involves more edge cases, for instance. So this is really a typical journey. By the way, all these transformer, estimator, evaluator, they're all kind of Spark specific terms. Like we said before, estimator is the kind of the model, the transformer is the machine learning algorithm, and the evaluator is what we use to kind of validate the model itself. Right, so let's look. So there's kind of 7 stages in this specific example, but as you can see, it's color coded. So it's still kind of train, test, deploy. So train is when you have the data and you train the model with, and then you test is when you do the testing, and then you deploy, you need to monitor, and then you need to maintain the model. So let's look at these stages sort of in details. Right, so in the first phase, we need to collect data, and we also need to pre-process them. There is so much going into this stage, and it is definitely not I would say it's almost the most important stage. You often hear in the sort of machine learning field, you often hear garbage in, garbage out. The quality of your training data is really, really essential to the quality of the models that come up as a result of your training data. So in this stage, we really want to watch for the things that could affect the quality of the data. So for instance, missing values, maybe the data is manually collected and there's some sort of missing fields, even though the schema has all of these things, but people might not some of the fields might be optional, so you get missing values. Quite often, let's say your business is particularly active in a certain region and you don't really have you don't really have sort of data in different regions. So if you're based in predominantly, let's say you're based in US West, for instance, then you might be lacking data in US East. And if you want to come up a model that is very generalized for all the regions, then you might see some problem with that data set. Also, the staleness of the data, so up-to-dateness, or how stale is your data, is also very important. Yeah. Like you can imagine, data is like vegetables, the fresher the better. So often you want to make sure that you're not training on, although it will still be relevant, but you don't want to train on data that's maybe like 20 years old, right? So in terms of all of these, what can we do, especially automatically or programmatically, to kind of counter these problems? So with missing values, there are a lot of metrics we can put in, a lot of checks. We can do schema validations, make sure that you have, it's a little bit similar to, how Java always have null pointer errors and you want to kind of get rid of them. With schemas, quite often you want to set fewer optional fields like possible, but that is not always possible because when you set a lot of non-optional fields, mandatory fields, that typically impacts your user experience. In my opinion, a lot of users really hate filling a big form when they try to, for instance, check out or book a restaurant on your app or something, and you do lose a lot of traffic if you do things like that. So there is always a balance to be had in those things. Imputations, for instance, you can also do when you encounter missing values. Skew and bias, we need to be aware of things like, the distribution of data. So you want to, I think the best thing there is really, firstly, you want to make sure the sample that you pick with your ideal distribution is the same as the actual data set you have. And also, I think in this step, quite often I find visualization is really, really the key, because if you can see the shape of the data, quite often it's a lot easier to spot the bias and the skew in those data. Up-to-dateness, again, there's things you can do. You can do a lot of pre-train validation. You can check dates. You can kind of have range of change checks as well. So range of change checks is for checking. Rate of change checks is for checking how frequent the data changes. So if the data does not change frequently, sometimes it can be a problem. If you expect, for instance, some data to be updated daily, let's say maybe transport data for London TfL, they might have data on various arrival and departure times of the trains and the tube system. And if the rate of change is less than a certain kind of rate, then there probably is some issue with the messaging pipeline or some of the streaming systems, because you do see like signal failures and things like that. So it might signal some upstream problem that would affect the data collection. So I guess that's probably enough for data collection and pre-processing. We can go into more detail if you have questions later on. The next stage, obviously, is model training and validation, or testing. In this phase, we would compute the resource that's needed to train the model. So a lot of the models nowadays, especially graph-based models, they're very, very resource intensive. So that's why you hear about things like TPUs, GPUs training, used for training and things like that. Not only that, sometimes pre-computation of the data sets also has a large, it eats up like compute resources like crazy. So you really need to make sure you provide enough computational resources in that stage. Also, we need to make sure that the testing is done after the model is trained. So we, like we said, we have a train test split for the data we collect, and then we use the test data set to validate the model afterwards. After the model is trained and tested and you're happy with the results, then we would then move on to publish the model with its metadata alongside the model itself. So the architecture of the model is very, very much dependent on what sort of data you have, and also what sort of project you have, right? Sometimes a binary classification is just good enough. Sometimes you want CNN, RNs, graph-based models. All of these is very much dependent on what sort of projects you have, what sort of also computational resources is available to compute those data as well, because quite often some of the more modern, what we call more modern, so maybe RN, CNN and graph-based models, they're a little bit more resource intensive versus the ones in the past. There are libraries, of course, that there's ways to do them, but you really would want to think about those availability or even like team availability before you compute all those things. So we really want to pay attention to, like I said, the computational resources, because I see a lot of I guess I'm also a little bit biased in this sense because I work in the ML compute side of things. So I see a lot of training failures, not because of data not being valid or the staleness of the data or the bias of the data. I see a lot of failures just due to pure kind of pure lack of resource. Quite often what happens would be if they compute on maybe a year's worth of data, it's cool, but it will fail if they increase the amount of data to be maybe 2 years or 3 years. So we really want to have a strategy in terms of, do you then partition the data? Do you maybe do some pre-processing just so any sort of computation resources you have could handle the amount of data that is coming in. Also, I guess the other thing which is kind of happening very often is if you either have too much or too little data, you would very often overfit or underfit the model. So you should see a peak of the performance of your model, and then it might drop. And after that drop, it means your model is overfitted. If you're not reaching the peak and it's increasing, the performance is increasing with the amount of data you're inputting, then it means the model is underfitted. That comes up really often. It's a simple thing to check for, and make sure you check for that. So we've kind of, just bear with me, we're reaching towards the end. So after training and testing the model, obviously we need to deploy it, and we also need to, the work is not done. Unfortunately, after you've deployed the model, it's in production. There's a lot that goes into post-deployment evaluation, because quite often the input data is not like we collect the data for the past year and it's done. It's always a continuous process. And like we said before, if your model is underfitted, the more data you get, the better the performance of the model would be. So in this stage, you would really need to look out for the performance of the model and also the drifts in the data quite often. For instance, the metrics we talked about before, for instance, knob value counts, rate of change, those metrics can actually vary significantly over time if there are some processes change during the time. Some people, like I said, iOS update might just trigger a drift if you're collecting images. If the presets are changed on phone cameras, things like that can all trigger a type of drift on the performance on the data. And also, there could be also manual processes. Maybe the team changed the structure or the way they collect data. All these can result in kind of performance degradation or some sort of drift. So you really want to. So in this sense, like ML is almost a bit of science and a bit of art almost. You really want to know what's changed and what's undocumented, especially, and you should not kind of restrain your thoughts to any sort of possibilities, because a lot of things can affect even the small things that you might even ignore in a lot of programmatical settings. Those things can typically kind of affect the performance of models and of the data itself. If you really have a very mature system, you could not only promote models to production when it passes a type of validation. If let's say if the accuracy is more than 95%, we promote the model to production. You could also have the same system that demote models when they have any sort of performance degradation. Again, based on the same principle, you could use the test data set to evaluate the model. And if, let's say, the accuracy is less than 90%, you're like, this is not good enough anymore, and let's demote the model. You blacklist the version of the model, and then you maybe roll back to a previous version, or you might just try to build up a new version of the model as quickly as possible. There are so many tools nowadays. I think the landscape has changed so dramatically in the past, I would say 5-6 years. Computational resources have got better. Docker has become a lot more mature. Kubernetes has also become a lot more mature, where everything is there kind of for you to implement large distributed systems in a programmatical manner. I'm sure a lot of you are familiar with the kind of idea of infrastructure as code, right? Which means nowadays you can just programmatically create computational resources on the go. You literally request so many EC2 instances just by like typing in one command, also programmatically. And especially with Kubernetes, it's not just EC2 instances. It might be databases, it might be volumes, it might be IP addresses. You can have loads of things just spun up on the go. With this, it really has provided a lot of possibility in continuous integration in machine learning, because I think the biggest sort of bottleneck in the past has been the fact that all of these things, firstly, they're not as robust, and also there are a lot more manual steps involved. But nowadays with Kubernetes, with things like Circle CI, Jenkins, GitHub Actions, Argo CD, all of these things, maybe some of you work with MLflow or maybe Kubeflow. All these things can help you to build such a pipeline where you collect your data, you train your model, you test your model, you validate it, you then deploy it, and you monitor, and then you repeat the whole cycle again, programmatically and automatically. So it's really the point of all these MLOps is there to build up this kind of pipeline and the system to make sure all these stages are happening continuously versus I write some code, I submit it, or like I upload a jar onto an EC2 instance. I let it run over the weekend. Maybe that's training the model. It doesn't have to be done like that. Nowadays, it's really the case that all of these can be done programmatically. And if you have a need, if you have more than one machine learning team, if you have more than one model, if you have more than one business problem that you think using machine learning to resolve would be beneficial, it probably would be a case that it's beneficial for you to have a team of ML ops alongside of the actual maybe data analysts or people who actually write the algorithms inside the training or inside the computation. So I guess I've spoken a lot about what MLOps are and what are the different stages and various steps that are commonly present in the whole ML continuous integration journey. I want to talk to you a little bit about how this is done at Yelp. And hopefully that would give you an even better hand or grip on the whole sort of landscape. Maybe it will still sound a little bit abstract, but hopefully the example of how MLOps is structured within Yelp gives you a better idea of the whole space. So like I said, we have Core ML, which is really the infrastructure of all the ML teams inside Yelp. And we have 3 sub-teams within Core ML. We have ML Compute, we have Model Platform, we have Feature Store. ML Compute is the team that I work for, that I'm actively participating in right now. At the moment, we're mainly focusing on on-demand cluster creation, on-demand compute provisioning. So it's really a platform for experimentation. What we provide with users are computational resources on the fly, so they can come to us, not necessarily come to us personally. They basically use our platform. They type in some commands. They can then start running experiments that might be using 1,000 pods just for one single experiment, because that's how much data they need to train on, they need to compute on. So it's really the ease of you request something within like 2 minutes. There's no process to go through. You don't have to fill in a spreadsheet. There's no and it terminates after the experimentation is finished, and we make sure the costs are controlled. No one's kind of wasting any resources, because this is very computational intensive. There's also the model platform. The model platform provides a lot of different libraries used for different model training. So there might be libraries that they maintain for, building a gradient boosted tree. There might be models, libraries they maintain for using RNN graph and things like that. We kind of try to gauge what is more popular within the wider company, and we maintain, obviously we try to maintain the ones that are the most popular, but we also kind of do some research on the side, and we test out whether certain libraries are mature or not for bringing into Yelp and for, I guess, pushing into production, because quite often some libraries, especially in the ML world, they come out of kind of research. But in terms of production readiness, it does not necessarily suit kind of companies that have like a whole kind of continuous integration pipeline. It might be more suitable for more kind of, not say manual projects, but projects that are a bit more ad hoc and more scratchy. So we really kind of want to look at what things are suitable for production and what things are going to be there for the best kind of business values. The third part of ML inside Yelp, core ML inside Yelp, is the feature store. It is so integral to the whole company. It's like a giant web that ties the whole company together by various schemas. Basically, we compute features and we maintain them. We check for the distribution of the data. We have lineages. We have schemas. We have validations. All these features are reusable. We also have access control on them. A lot of these features might be sensitive, so we have some sort of I guess blurring, if that's the word to use, but basically it makes it less visible to see all the personal information. So if it's particularly personal, the data that is personal will be kind of blurred in a computational sense. And really, these are the three major teams inside core ML, and pretty much covers the whole kind of ML ops landscape inside Yelp. All right, let's summarize. We're kind of coming to the end of this talk. I guess we talked about what continuous integration looks like for machine learning, how it differs from traditional DevOps, how it's similar to also the traditional kind of continuous integration for normal services that don't use a lot of data, don't use a lot of training. I used to work in backend a lot, where it's all about APIs, and most of the time, if it's building some sort of web service, it's always kind of, you grab some data from the database, you try to churn out a few APIs on those data, you push it to production, and that's really a continuous integration cycle, where the main thing you would test is kind of the schemas on the API, the responsiveness, maybe the request limits and things like that. All these are still valid, because typically a machine learning model will be a sort of API-based service. So it will be kind of accepting some sort of input, whether it's an image, whether it's a blob of text, and then it will have some output, typically still done in either maybe protobuf or some sort of REST API. So all of the things that you know about traditional web services, they're all still valid. But machine learning, really the added on is the data collection, which is sometimes far more important than the actual training stage. Making sure the shape of the data is correct, the distribution of the data is correct. And then you train the model. Whilst you're training, you have to train as well as validate after you've trained the model. Not everything can be pushed into production if the model doesn't pass it doesn't pass a certain kind of accuracy, you would have to get rid of it. After productionization, you would have to continuously monitor your model and make sure the performance of the model is up to a certain standard. You can, like we talked about before, you can also implement things that demote model continuously if it degrades, if the performance degrades over a certain time. So we've also talked about how kind of MLOps looks like inside Yelp, and CoreML is the team. It's a team that serves as a horizontal layer and provides common functions to support all other ML teams to achieve efficiency and performance. Hopefully you enjoyed the talk, and hopefully if you're not yet at MLOps, maybe you already work with MLOps, or maybe you're a DevOps. If you liked what you saw, also, I would like to say Yelp is hiring. Feel free to add me on LinkedIn. You can search for my name with Yelp. There's lots of positions within the CoreML team available. Yeah, I hope you could consider this as an option potentially in the future. But anyways, I really hope you enjoyed the talk, and thank you very much for being here. Thank you. So with all of this, let's go into questions.
Yeah, so thank you very much, Leah. First of all, a really informative and in-depth webinar, I think. So yeah, that was great. I know I really enjoyed that a lot. And just to kind of add to what you're saying, just a quick reminder for everyone to go onto Showcode and sign up there and follow the Yelp hub there as well, because I'm sure we'll be posting lots of exciting things there as well. And just I think while we're waiting to see if there are any kind of questions, I think I'd like to ask you if you maybe have any tips or advice for people going into the Athena hackathon this weekend, just from your side as a software engineer. And
yeah, sure. Right, hackathon. Yeah, I guess first thing, I would treat hackathons as a safe space for experimentation. I think a lot of the times, because you're pressed by kind of business value, revenue, deadlines, and things like that, there are things you want to learn, and there's things you want to almost play with that you feel maybe is not suitable to bring into your kind of day-to-day job. So I think hackathons is really a good place to experiment with those things. And especially it might be a technology you want to try out, maybe ML, you might want to like build your very first machine learning model, something like that. I really think it's absolutely a great place to start with something that you're very, very interested in, but don't really get a chance to do during your day-to-day life. The other thing is, I think hackathon is all about people. It's really, most of the projects will be kind of team-based. So it's really a place for teamwork and networking, socializing, and meeting great people. So that will be, I guess that will be my 2 pieces of advice.
Yeah, that's brilliant. That's great. I love that. So thank you so much again, Lee. And I'm just looking at the chat, and I can't see any questions at the moment, but I think what we can do, if anyone kind of thinks of anything,
sure.
They can post their questions on Discord as well, or get in touch with us kind of via email or any
sure.
other means
Sure.
if there are any questions that kind of come up after. So yeah, everyone just don't be shy, and yeah, let us know if you have any questions afterwards. And thank you so much for watching, everyone, and hope you all have an amazing day.
Thank you all.